Hi everyone, welcome to my presentation. My name is Shanzhao Di, and today I will be presenting my MAT 202 coursework project. The topic of my presentation is limit of a sequence, proving limits using epsilon n arguments. Here is a brief outline of our journey today. Firstly, we will review the background and the formal definition. Next, we will dive into a rigorous proof demonstration using a concrete example. After that, I will summarize a universal proof strategy, and finally, we will conclude with key takeaways. Let's start with the background. In calculus, we are often told that the sequence converges if its terms get closer and closer to limits. But in mathematical analysis, this intuition is fundamentally false. What we do is complex multi-dimensional spaces. To fix this, Cauchy and Weierstrass introduced the rigorous epsilon n argument. Instead of asking where is the sequence going, we change our perspective and ask, can we trap the sequence within arbitrary small error bounds? Since our course focuses on multivariable analysis, let's look at the formal definition in RM. A sequence X sub k converges to limits vector V if for every real number epsilon greater than 0, there exists a natural number n such that for all integers k strictly greater than n, the Euclidean distance between x sub k and v is less than epsilon. There are three core components here: the arbitrary error margin epsilon and the Euclidean Euclidean distance and the specific index threshold that we need to find. To understand this better, let's look at the geometry visualization. The red dashed circle represents our epsilon neighborhood around the limit of V. The goal of our proof is to find that specific threshold, and as you can see, once we parse the index in, all the subsequent vectors represented by the blue dots fall strictly inside the red circle. Now let's apply this to a concrete problem. We want to evaluate the sequence in R2. Consider the sequence x sub k equals 1 over k and 2k minus 1 over k plus 1. We need to rigorously prove that its limit is 0, 2. To do this efficiently, I will use a two-step approach. First, we need the scratch work to discover our n, and the second, constructing the formal logical proof. Let's firstly begin with the scratch work. Let epsilon be greater than 0. We need to evaluate the difference vector between s sub k and our limit v by subtracting 0, 2 from our sequence terms and finding the common denominator for the second component. We simplify the difference vector down to 1 over k and negative 3 over k plus 1. Next, we compute the norm. We get the square root of 1 over k squared plus 9 over k plus 1 squared. Now here is the crucial analytical step. Working directly with this abstract expression is algebraically messy. Instead, we should use the art of bounding. We know that k plus 1 is strictly greater than k. Therefore, taking the reciprocal squares, we can deduce that 1 over k plus 1 square is strictly less than 1 over k squared. Then by applying this inequality, we overestimate our distance. We replaced k plus 1 square with k square, which is simplifies our bound to square root of 10 over k. To guarantee our distance is less than epsilon, it is sufficient to force this simple bound to be less than epsilon. So when this gives us k is larger than square root over 10 over epsilon. And just like that, our square work is done. The threshold n must be an integer greater than the square root of 10 over epsilon. Now let's reverse the logic to present a flawless mathematical argument. Let epsilon be greater than 0 by the Archimedean property of real numbers, since the square root of 10 over epsilon is a positive real number. There exists a natural number n that is strictly greater than it. Suppose k is any natural number greater than n by transitivity. K is also greater than the square root of 10 over epsilon. Rearranging this inequality, we establish that square root of 10 over k is smaller than epsilon. Now we evaluate the exact Euclidean distance between our sequence and the limit 0 2, which will give us our original square root expression. Using our bounding technique where we substitute k plus 1 square with k square, we can show that this distance is strictly less than the square root of 10 over k, since we already established that square root of 10 over k is smaller than epsilon. We can logically conclude that the distance is strictly less than. Thus, by the formal definition, the proof is complete. Reflecting on this example, we can distill a universal point for the direct epsilon n methods. First, always acknowledge that the arbitrary error margin by stating that epsilon is larger than 0 be given. Second, manipulate and bound the distance expression. Thirdly, find the n in terms of epsilon. And fourth, write the formal proof forward to verify it. My pro tip here is do not skip step 2. Properly bounding the expression is a core mechanism that prevents your algebra from becoming unsolvable. To conclude, proving a sequence limit requires absolute logical rigor, not just intuition. The hallmark of analytical maturity is mastering the power of inequalities and bounding techniques. Furthermore, a valid proof must have a flawless logical structure. Heavily relying on axioms like the Archimedean property. Finally, as we demonstrated, this logic is universally powerful, applying seamlessly to multidimensional spaces. Here are the main references I used. Thank you so much for your time and attention. I'm open to any questions.